This is Shivadharam signing in, and I am here to explain you about dielectric heating in this session. Dielectric heating is nothing but heating of the insulators like paper, wood, rubber, etc. In this method, the insulating material which is to be heated will be subjected to a very high voltage electric field, alternating electric field. When this alternating supply is given to a dielectric material, the atoms are going to be subjected to dielectric stress, because in alternating we know that for half of the time it will be in one direction, and for the remaining half of the time it will be in the opposite direction. So because of this, what actually happens is the atoms are going to be the alignment of these charges, that is positive charge and negative charges of an atom, are going to be distributed randomly as the fields are going to be reversed, that is in positive half cycle and negative half cycle. Because of this, the atoms are going to be subjected to some internal stress which is responsible to create the dielectric loss. In turn, this is going to develop the required heat energy. Let me go through the details. So here, after the completion of this topic, we are going to learn about dielectric heating and also the advantages and disadvantages, applications of dielectric heating. So as we have already seen that whenever an insulating material is subjected to an alternating electric field, the atoms get stressed, and due to the interatomic friction caused by the repeated deformation, the heat is going to be produced. And this is also known as dielectric loss. This dielectric loss is dependent upon the frequency and high voltage that we are going to apply. Here the frequency will be of the order of, actually we cannot go on increase the voltage beyond a certain limit due to certain constraints. So that is the reason why the method that we are going to employ for this dielectric heating is with increased values of frequencies. Something like, the frequency will be of the order of some megahertz. So generally the range of frequencies will be 10 to 30 mega cycles per second. Or if we need to apply the high voltage, the voltage we have to apply for this particular application is about 20,000 volts or 20 kilovolts, which will be somewhat difficult for us. So generally we know in the case of magnetism, the hysteresis loss is going to happen because of the reversals of magnetism. So in the same way here also we are going to have the dielectric loss for this particular method of heating whenever the material is subjected to alternating electric field. So generally the centers of positive charge and negative charge are actually coincident when the atom is considered, when a neutral atom is considered, that is when with no external electric field. So we are going to have this as the neutral atom, where inside the nucleus we are going to have the positive charge, and the negative charge is going to be distributed like this. So this is considered as neutral atom without any electric field, external electric field. But once the electric field is applied, so the two effective centers of positive and negative charges are going to be moved a little bit. So this is this condition of the atom is said to be polarized, and here you can observe for one half of the cycle, say this is positive and this is negative, the positive charge is going to be moved towards the negative plate or negative part, and whereas the electrons, whatever negative charge is there, the center of negative charge is there, that is going to be moved towards the positive, that is anode. So this is known as actually the electric dipole moment, because we here assume that the two charge centers are going to be a little bit, are kept a little bit distance of, say, some d distance, the effective centers of both positive and negative charges, and as a result we are going to have, so like this. Here this is the effective negative charge and this is effective positive charge, which are going to be aligned at a distance of d because of this applied electric field. and here this dipole moment is going to be calculated as q into d. Q is the charge and d is the distance between the effective centers of positive and negative. So here in this condition the atom is said to be polarized, and as the electric field strength is increased, the degree of polarization also increases. So after attaining a certain value of electric field, these electric dipoles of the electric material will align themselves in this fashion. So here when AC supply is given beyond at a particular voltage, the atoms are going to be aligned in this fashion. So here this diagram shows the effective centers of negative and positive aligned themselves in this fashion. So this is positive and this is negative. As you can see, in each atom the negative is moved a little bit towards positive, and the positive charges, the effective positive charge is moved towards the negative electrode. So here some of the energy applied will be wasted towards the interatomic friction. So what actually here what happens is two things are going to be fulfilled for us. One is one part of the current will be used is going to be used towards interatomic friction, or which is responsible for dielectric loss, and another one is to charge that particular material. So we are going to have two components of current. So obviously it is desirable to apply high voltage, but not to apply high voltage, but use high frequencies. So this is one important aspect of this particular method. Here the total current we are going to draw is going to be considered as two components. One is IR, which is responsible to have this dielectric loss. Another one is the charging current. So whatever capacitance is there that we are going to have for this particular both cathode and anode. So that this is the charging current, which is, so these two currents we are going to have here. And as we know that this capacitor current is going to lead this voltage by 90 degrees, whereas this whatever loss component, dielectric loss component of current is there, this is resistive component, and that will be in phase with the supply voltage. So here we can have the phasor diagram for this. If we take V as the reference vector and I is the total current, let us say phi is the phase angle between voltage and current. Cos phi, as we know that this is the power factor. IR will be in phase with the supply voltage, and IC will be in 90 degrees leading with respect to the reference, that is voltage. So here delta is considered as dielectric loss angle, which is equal to 90 minus phi. This is one of the important aspects of this particular method. Now the total current is the combination of these two currents, IR and IC. As we know, the capacitive current leads by 90 degrees and the resistive current will be in phase with the supply voltage. Now let us see the derivation which is involved in this particular dielectric loss. So here the loss is nothing but the useful component of power, which is equal to Vi cos phi, where I cos phi is the in phase component of the total current I. So which is IR here. So V into IR. But at the same time, if you see the previous diagram, here IR is going to be, this is IC, this component of this is total current I, IC will be equal to I cos delta, and IR will be equal to I sin delta. And if you find out tan delta here, tan delta will be equal to, you can see here, IR by IC. So from this, what actually tan delta is equal to IR by IC, and you can have the value of IR as equal to IC into tan delta. So this is what I am substituting here. So IR is equal to IC tan delta, and IC is equal to again V by XC, the supply voltage divided by the capacitive reactance multiplied by tan delta. So V into V multiplied by V gives us V square, and we know that 1 by XC is nothing but omega C, because the capacitive reactance XC is equal to 1 by omega C. Hence here 1 by XC becomes equal to omega C, and tan delta. Of course, for smaller values of delta, we are going to have the value of tan delta is equal to delta. So finally the formula is going to become, for dielectric loss, as equal to V square omega into V. Omega is, we know that 2 pi f. Omega is going to be 2 pi f, and the value of capacitance of the capacitor is going to be epsilon naught into epsilon r into A by D. Epsilon naught is actually the permittivity of free space, or A. So that is one, as we know, that 8.854 into 10 to the power of minus 12 farads per meter, and epsilon r is the relative permittivity. A is the area of that particular area of cross section, and delta is the dielectric loss angle divided by D is the distance between the two plates. So this is the final formula for finding out the dielectric loss by this method. So here V is the applied voltage, and F is the frequency. Epsilon naught is absolute permittivity, which is equal to 8.854 into 10 to the power of minus 12, minus 12 farads per meter, and epsilon r is the relative permittivity of the medium. Actually this will be 1 for the free space, or area of the plate or electrode, which is in square meter, and D is the thickness of the dielectric medium or distance between the electrodes, and delta is the loss angle, which is represented in radians, and this is loss factor. So finally the dielectric loss is proportional to square of the supply voltage or proportional to the frequency. So here this loss can be varied by either varying the supply voltage or the frequency. So under normal conditions, the voltage gradient is limited to 18 kilovolts per centimeter. So this is very huge value. So that is the reason why we are going to use high frequency for dielectric heating. So generally the frequency that we are going to use will be in the range of some 1 to 40 megahertz. Mega means in 10 power 6. So that's about the dielectric method of heating. If you go for the applications, we are going to use this method for dyeing of tobacco, paper, wood and rayon, welding of PVC, stress annealing textile fibers, and heating of bones and tissues, gluing and bonding of woods, sterilization of sterols and medical equipment, and also processing of rubber, synthetic materials and chemicals during manufacture. Heat sealing of plastic resins, these are the applications. Preparation of thermoplastic resins, and sewing of raincoats, umbrellas made of plastic film materials, and diathermy treatment of certain body paints and diseases, etc. So these are the advantages we are going to have with the dielectric heating. Heat is produced in the whole mass of the material. So this is one of the major advantages we are going to have with the dielectric heating compared to other methods. And this is the method which is employed for heating the non-conducting materials in a very fast way, and we are going to achieve the uniform heating also. So these are certain advantages we are going to have. And generally the frequency, the questions which are going to be asked frequently are what is dielectric heating, and the ranges of voltages and frequency. These are the short answer questions we are going to have, and explain the process of dielectric heating. So here it involves the entire procedure and also the diagrams which are involved to explain this method. And in addition to that, we have to go for the derivation also for the dielectric loss. Just now we have seen applications and advantages. So these are certain questions. That's all for today's session. The next class I am going to give you some more information regarding electrical utilization. Subscribe to my channel and give your valuable feedback. Thank you very much. This is Shiva Biram signing off.